Welcome to the Problems channel, Season 1, Episode 9, the episode in which we will discuss the solution of the problem S1M10. This is also the last episode of the first season, and just in 8 previous episodes, we actually managed to learn quite a bit. We now know what is mathematics, we know what mathematics is not, and we know what is not mathematics. We know the difference between a mathematical exercise and a mathematical problem. We know how to practice mathematics correctly. We so far have studied the mechanics of the transform and conquer problem-solving approach, and right now we're in the middle of studying the so-called reinterpret and conquer problem-solving approach. In this particular problem, we're asked to find an alternative representation or a synonym for the real number that is attached to the finite sum shown in the upper right corner of the board over here. Again, no one in the mathematical community cares about the actual number in the big scope of things and in a good way in general, but everyone in mathematical community does care a lot about your ability to generate a story of how and why this particular real number or a synonym real number comes into existence. Purely because of the placement of this exercise in our sequence, it is evident that one way to solve this problem is to apply the reinterpret and conquer problem-solving approach to it. According to the reinterpret and conquer problem-solving approach, we should try to look for a different interpretation or for reinterpretation of the local subject matter that possesses the following two fundamental properties. The candidate reinterpretation should preserve the technical essence of the original problem, because we want to solve this particular problem and no other. And the candidate reinterpretation should provide us with a tactical advantage that will make the search for a solution of a reinterpreted problem more tractable and more straightforward. In this particular case, what a successful or what a fruitful reinterpretation of the local subject matter at hand could be? Well, we know that mathematics, first and foremost, is an art of telling a story of how and why. Later on, mathematics, or in parallel, mathematics becomes an art of telling a story of how and why wrapped into the language of three logical connectives, not and or, two quantifiers, existential and universal, and an implication, if P then Q. Later on yet, or also in parallel, mathematics becomes the study of structure divorced from any specific context. As such, let us try to think like a mathematician when we're trying to solve this particular problem. The number k over here is real. The number pi is real. The number 11 is real. A product of any two real numbers is a real number, and the ratio of two real numbers, of which the number in the denominator is not zero, is a real number. The trigonometric function of cotangent maps consequently real numbers to real numbers. A square of a real number is a real number, and the sum, in this case, of 5 real numbers is back again a real number. In general, a real number can have a large number of alternative or possible different interpretations. For example, a real number could be a distance, it could be an area, it could be a volume, it could be a mass, and it could be time or temperature or density, borrowing some of the notations from physics, for example, or it could be a probability if it's scaled appropriately and belongs to the range of real numbers 0 to 1. But in general, as we noted earlier, the reinterpret and conquer problem-solving approach is much more subtle, because reinterpretation of just about anything in just about any other endeavor can be very subtle, because for the said reinterpretation, only a slight change of the angle of view or a slight change in the perspective is enough to come up with a different interpretation of the matter at hand. Consequently, in this particular case, we can come up with an idea that these specific real numbers may be roots of a single variable polynomial over the field of real numbers. This idea, of course, in real time will not visit us right away. We will try and fail several times looking for a successful reinterpretation. And that process is what precisely constitutes, in this stage and for us, the process of doing mathematics. As such, let us say that we manage to come up with the polynomial in a single variable x that has the following shape: a sub n, x to the nth power, a sub n minus 1, x to the power of n minus 1, plus so on, plus a sub 2, x squared, plus a 1, x, plus a sub 0. What does this particular polynomial has to offer? Well, we know that if these numbers, for example, can be interpreted as the roots of such a polynomial, then these specific roots, and hence these specific numbers, must dance to the music of the Vieta's formulas. And the Vieta's formulas provide various computational shortcuts to various algebraic expressions that involve precisely the roots of a polynomial. For example, we remember that for the sum of roots, let's say we designate each number over here as r sub k for a root of a polynomial. Then for the sum of roots of such a polynomial, according to the Vieta's formulas, we have the following fearless prediction: negative ratio of a sub n minus 1 over n. And for the product of these roots, we have the following fearless prediction: minus 1 to the power of n, and the ratio a sub 0 over a sub n. Now, in our notation, a sub 0 represents the least senior coefficient. The number a sub n represents the most senior coefficient, and the number a sub n minus 1 represents the next most senior coefficient. Consequently, if we manage to construct a mystery polynomial whose roots are precisely the numbers in the given finite sum, then we can use the Vieta's formula for the sum of the roots of such a polynomial and, sort of free of charge, obtain the answer to the current problem. In addition, we can also compute the product of these roots and some other combinations that are provided by the Vieta's formula. However, the wonderful way in which mathematics works, if we just take the sum of roots, we in theory do not really need to recover the entire shape of the polynomial in a single variable over the field of real numbers, because in order to solve the problem at hand, all we need to do is recover the shape of the most senior coefficient a sub 1 and the shape of the next most senior coefficient a n sub 1, and in theory we do not really need to recover the entire shape of the polynomial at hand. As such, we carefully note that this initial process of generating and regenerating ideas, combining and recombining ideas, trying and failing, is precisely the process of doing mathematics, and we think that this idea represents a successful reinterpretation of the matter at hand. Now, according to the Reinterpret and Conquer problem-solving approach, our reinterpretation should possess two fundamental qualities. It should preserve the technical essence of the problem at hand, and it should provide a tactical advantage that will allow us to solve a reinterpreted problem in a straightforward manner. Does our idea honor the requirements imposed on this idea by the Reinterpret and Conquer problem-solving approach? Well, the answer to both of these questions is yes. We're given several, or 5 to be exact, real numbers in this finite sum. These real numbers still remain or stay real numbers, and the essence of the fact that these numbers are real doesn't change simply because we apply the Vietas formulas to these numbers if these numbers are interpreted as the roots of the polynomial shown over here. Now, does this reinterpretation afford us a tactical advantage? The answer to that question is also yes. However, we need to figure out how, based on our reinterpretation idea and given the specific shape of the real numbers at hand, we can construct a polynomial whose roots will be precisely the given real numbers. Well, that can be done using the following two fundamental units of mathematical knowledge. First of all, we will need the so-called binomial theorem that holds for real numbers x, y, and non-negative whole numbers n, and that particular expression can be also written as a sum over k varying from 0 to n of the binomial coefficients n choose k, and then x raised to the power n minus k times y raised to the power k, or equivalently, that expression can be represented as a finite sum over k varying from 0 to n of binomial coefficients n choose k when x is raised to the power of k and y is raised to the power n minus k. For real numbers x and y, there exists a beautiful combinatorial proof for that particular mathematical fact, but for now we'll take it as a given without a proof. The second basic unit of mathematical knowledge that we will need in this case is the so-called de Moivre's formula, or de Moivre's theorem, which states that cosine of theta plus I sine of theta raised to the power n, which could be a negative whole number, 0, or positive real number, and that is equals to cosine of n theta plus I sine of n theta. Here, this particular identity holds for all real numbers theta and for all integers n, which could be again negative whole numbers, 0, or positive whole numbers. That particular identity should not be too mysterious because the number in the parentheses here is a complex number that geometrically corresponds to a point in the complex plane that sits on the periphery of the origin-centered unit circle, and when it raised, for example, to a positive integral power, then the result is also corresponds to a point in the complex plane that sits on the same origin-centered unit circle, but rotated with respect to the original point. Now we apply the binomial expansion to the expression in this formula shown on its left-hand side. When we treat, for example, which one is more convenient here? This one is more convenient because here we will be raising I to some powers that will vary, so we will associate x with cosine and we'll associate y with this whole expression over here. But because this expression expanded binomially will be exactly the same as the expression shown on the right-hand side, we can write cosine of n theta plus I sine of n theta equals to the sum over k, which varies from 0 to n, of the binomial coefficient n, choose k, times what? Times cosine of the angle theta raised to the power n minus k, times what? I raised to the power of k, times sine of theta raised to the power of k. Again, this particular step should cause no problems because we obtain that step by simply applying this binomial expansion to this expression over here. Now, in this expression, let us try to get a hold of what is really going on here. The powers of the trigonometric function of cosine behave in a predictable way. We understand what's going on here. The powers of the trigonometric function of sine behave in a predictable way. We do understand what is going on here. Now let us try to wrap our brains around what is going on with the imaginary unit I raised to the power of k. Here the situation is not particularly difficult if we recall that to every complex number there corresponds a unique point in the complex plane, and conversely, to every point in the complex plane there corresponds a unique complex number. In this case, the complex number I geometrically can be, let me write it down here, geometrically can be represented as a point on the origin-centered unit circle. This will be 1, this will be negative 1, this will be negative I, this will be positive I. This is real numbers, these are imaginary numbers. In this case, the complex number I can be represented by a point that is located in the complex plane and is positioned on the periphery of the origin-centered unit circle. In particular, this point will sit on the imaginary axis over here. Now, the fact that we raise this particular number I to a positive integral exponent or power means that it is possible to interpret the act of raising a number I, the number I, to the positive integral power as the multiplication of the complex number I by itself in this case. And geometrically, the algebraic operation of multiplication of one complex number by another corresponds to a commutative composition of two geometric transformations. the homothety of the complex plane with respect to the origin and the rotation of the complex plane about the origin as well. However, the modulus of the complex number I is 1, which means that if we multiply the complex number I, for example, by itself, we simply, if we multiply a complex number by itself algebraically, that means that geometrically, we simply rotate the corresponding point about the origin counterclockwise by the principal argument of that complex number, which is pi over 2 radians. So, for example, I squared lands us on the point -1. Consequently, we conclude that when I is raised to the integral power k, what will happen? If k is congruent to 0 mod 4, then I raised to the power of k will generate +1. That means that all the integral even numbers k in the shape of 0, 4, 8, 12, and so on will convert the imaginary number I raised to such a power into a positive unity. For example, I squared, that corresponds to raising the number I to the second power. I cubed puts us over here, and I raised to the fourth power puts us on the point 1. From here we simply count 5, 6, 7, 8, 1, 9, 10, 11, 12, 1 again, and that is what we captured with this notation over here. Likewise, if k will be congruent to 2 mod 4, then I raised to the power of k will generate -1, which means that all the even numbers in the shape 2, 6, 10, 14, 18, 22, and so on will convert the imaginary unit I raised to that power into a negative unity. For example, we already know that I squared generates -1, and then we count starting from that point. 3, 4, 5, 6, -1. 7, 8, 9, 10, -1. 11, 12, 13, 14, -1, and so on. And what will happen with the odd positive powers of I, because k over here varies consecutively from 0 to n, so that means that the parity of that number will flip odd, even, odd, even, odd, even. We notice from this particular diagram that if k is congruent to 1 mod 4, then I raised to the power of k will generate positive I, which means that all the positive odd numbers k in the shape 1, 5, 9, 13, 17, 21, and so on will convert the imaginary unit I raised to that power into positive I. That should be evident from our simple experiment like so. I raised to the first power is obviously I, and then we count 2, 3, 4, 5 I, 6, 7, 8, 9 I again, 10, 11, 12, 13 I again, and that is the fact that we captured over here. Lastly, if k is congruent to 3 mod 4, then I raised to the power of k will generate -I. Again, that means that all the positive odd numbers k in the shape of 3, 7, 11, 15, 19, and so on will convert the imaginary unit I raised to that power into negative imaginary unit or negative I. That much also should be evident from this diagram, because if we start with the point over here, negative I, and then we count 3, 4, 5, 6, 7, negative I, 8, 9, 10, 11, negative I, and so on. Now that we understand how the imaginary unit I raised to the integral power k will behave, we can spell out, let me erase this, we can spell out this particular binomial expansion by observing that no matter how the variable k changes in this particular binomial expansion, it will either become plus or minus 1, or it will become plus or minus y. And what does that mean? That means that all the summands in this binomial expansion can be sorted into two neat piles. In one such pile, each and every summand will be I free, or will not have the factor of I in that summand, because that power of I will be replaced with plus 1 or negative 1. And in the second such pile, each and every term will be I bound, or it will have precisely one factor of I, which, as we understand, will be with the positive or a negative sign, depending on the specific value of the integer k. And that means that all the summands that are I-free in this expansion can be attached to the only term on the left-hand side of this equality that is I-free, and consequently all the summands in this binomial expansion that are I-bound, that will have plus I or minus I in them, can be associated with the only I-bound summand that is located on the left-hand side of this equality. Consequently, we can write, for example, that cosine of n theta will be equal to the I-free pile in this expansion. That is, it will be n choose 0 for the binomial coefficient, then it will be cosine of theta raised to the nth power, then it will be minus n choose 2 for the binomial coefficient, then it will be cosine of theta raised to the power n minus 2 times the sine of theta raised to the second power. This is this case over here. What will the next term be? Well, the next term will be plus n choose 4 for the binomial coefficient, and so on. Likewise, for the sine of n theta, we will have what? For the sine of n theta, we'll technically have the imaginary unit I over here, but because each and every summand in this expansion, remember, will carry positive I or negative I, these i's will cancel out, so we might as well write the expression for sine of n theta right away. Here in this expansion over here, the bottom numbers for the corresponding binomial coefficients are even, 0, 2, 4, and so on, in the correspondence with this observation. And the corresponding numbers for the sine of n theta expansion will be odd in the correspondence with this observation. As such, for the sine of n theta, what will we have? We will have the coefficient, the binomial coefficient n choose 1 times cosine of theta raised to the power n minus 1 times sine of theta. For the k equals 1, then it will be minus n choose 3 for the binomial coefficient. multiplied by the cosine of theta raised to the power n minus 3 times the sine of theta raised to the power of 3, k, plus what? The binomial coefficient n choose 5 times the cosine of theta raised to the power n minus 5 times the sine of theta raised to the power of 5. Again, this is the coefficient k spelled out as 5. The next term will be minus n choose 7, and so on. Now, across these two expressions for the cosine of n theta and the sine n theta, which one is more tactically advantageous to us? Well, again, here we will not, in real time, we will likely not understand right away what is going on. We'll try and fail several times, but upon thinking about it, trying and failing, it becomes evident that it is this expression that will be helpful in this specific problem. Why is that? Well, let us analyze the powers of the trigonometric functions of cosine and sine in each of these summands. Notice that the total sum of these powers comes out to n, because here the total sum will be given by n minus 1 plus 1, n. For this summand, what will we have for the total sum of the powers? N minus 3 plus 3, n. For the next summand, n minus 5 plus 5, n again. And what does that mean? That means that we can multiply and divide each such summand by the trigonometric function of sine of theta that is raised to the power n. What will happen if we do that for the very first term? Well, in this case, we will have our binomial coefficient n choose 1 times cosine raised to the power n minus 1 of theta times sine of theta divided by sine of theta raised to the power n and multiplied by the sine of theta raised to the power n. Again, that maneuver should be very transparent because these two numbers in the numerator and denominator will cancel each other out and thus will not change the overall value of the first summand. However, what advantageous situation do we have now with this summand? Well, we see that if we cancel this sign in the numerator and borrow it from here, and the power of this sign will become n minus 1, what will happen? What will happen is that we will carry our n choose 1 binomial coefficient as it was, but then we will say that this will be equal to cosine of theta raised to the power negative 1 divided by sine of theta raised to the power n minus 1 times sine of theta raised to the power of n. And what do we see now here? Well, we see that we managed to manufacture precisely the trigonometric function that we're given in this specific problem. Because according to the middle school definition of the trigonometric function of cotangent, that function is represented as a ratio of the cosine of the angle theta to the sine of the angle theta. In other words, what we have here is our binomial coefficient n choose 1 times cotangent raised to the power negative 1 of theta times sine of the angle theta raised to the power of n. Again, this particular string of manipulations is quite straightforward. Nothing over here is beyond the average middle school arithmetic. It should be straightforward to comprehend. But now we understand that when we apply the same maneuver of multiplying each and every summand in this expansion by sine of the angle theta raised to the power of n, we will obtain the overall expression of this specific shape. For example, let me erase, now that you guys understand what is going on, let me erase this to make some room. And let us together analyze, for example, the second summand in this case, after we apply to it the maneuver of multiplying and dividing that summand by this number. What will happen over here? Well, we will have our n choose 3 as the binomial coefficient. We will have the cosine raised to the power n minus 3. We'll have sine of the angle theta cubed divided by sine of theta raised to the power n times multiplied by the same sine of angle theta raised to the power n. Again, we took the second summand in this expansion and multiplied and divided it by one and the same real number. Whether this real number can be 0 or not, for now we ignore and we operate here purely formally. What will happen over here? Well, again, we cancel out this sine of the angle theta raised to the third power, borrow these 3 powers from here, and then we see that when we move the sine of the angle theta in this particular power under the cosine, we again manufacture precisely the trigonometric function of cotangent, and we can write right away that here we will have n choose 3 for the binomial coefficient. Cosine over sine will give us cotangent of the angle theta to the power n minus 3 times sine of the angle theta raised to the power of n. This is the result of the application of this maneuver to the second summand in the expansion of the sine of n theta. Now, if we skip these intermediate manipulations, can we name the result of the application of that maneuver to this summand in the expansion? Well, we already see that it shouldn't be too difficult to write down, for example, this guy in the following form. N choose 5 will be the binomial coefficient. No change here. When we multiply this summand by the sine of the angle theta raised to the power of n and divide it by the same number, we again will cancel out the sine of the angle theta raised to the 5th power, borrow these 5 powers from the sine in the denominator, coalesce it with the cosine that is raised to exactly the same power, manufacture the trigonometric function that we're given, and we will have cotangent raised to the power n minus 5 of the angle theta times sine of the angle theta raised to the power of n. Now, do we see what kind of pattern is unfolding in all these manipulations that leave this expansion in its original shape? Yes, we see that after we carry out this manipulation with all the summands, we will have this factor, sine of the angle theta raised to the power n, as shown over here, as a common factor. And what does that mean? That means that we can rewrite this expression over here in its equivalent form as follows. Carrying the common factor of sine of the angle theta raised to the power of n out of all the summands, we will have sine of the angle theta as a common factor raised to the power of n, and let's say in the square parentheses, just to provide some visual appeal and to make things easier to distinguish, we'll have the binomial coefficient n choose 1 times cotangent raised to the power n minus 1 minus the binomial coefficient n choose 3 times the cotangent of the angle theta raised to the power n minus 3 plus n choose 5 times the cotangent of the angle theta raised to the power n minus 5 minus n choose 7 and so on. Again, just to take a short breather, we in this problem are asked to find a synonym or an alternative expression for the following finite sum. Our idea of applying the reinterpret and conquer problem-solving approach to the solution of this problem amounted to a happy thought after several trials and failures to reinterpret these numbers as the roots of a mystery polynomial, which then can be summed straightforwardly using the Vieta's theorem. And we expanded the de Moivre's relation on the one side as it was, and on the other side according to the binomial expansion shown over here. We carried out the maneuver of multiplying and dividing each resultant summand over here by one and the same real number, and this is the expression that we have over here right now. How does it get us closer to the solution of the problem? Well, now we want to manufacture convenient powers of the trigonometric function of cotangent, because remember that it's not just the cotangent itself, it's the cotangent squared is given to us in this specific problem. So how can we manufacture the cotangent squared in this case? Well, let us think about it. What if we again think like a mathematician? What if the number n is actually odd, which means that what if the number n is representable as 2m plus 1 for a suitable integer m? What will happen in this case? Let us analyze these powers of the trigonometric function of cotangent, what these powers will look like. Let us work with the first power. N minus 1 will be equals to m plus 1 minus 1, and that means that here 1 and 1 will cancel out. We will be left only with the number 2m, which can be represented as 2 times m minus 0. Very well. Let us work with the next power, n minus 3. What will happen here in this case? N minus 3 will be 2m plus 1 minus 3 equals 2m minus 2. And how can this number be represented alternatively? Well, yes, it is 2 times m minus 1. So now we already see, something is advantageous going on. M minus 0, m minus 1. What will happen with the next power of the trigonometric function of cotangent? Let us investigate. N minus 5 equals 2m plus 1 minus 5 equals 2m minus 4. And how can this number be represented alternatively? Correct. We can write this number as 2 times m minus 2. The next power over here will be what? N minus 7. And that will be 2m plus 1 minus 7 equals 2m minus 6. That can be represented as 2 times m minus 3. So now we have a nice pattern of diminishing numbers m in exactly the way in which the powers in a mystery polynomial diminish. In other words, if the non-negative, let's say, whole number is representable as 2m plus 1, or if that number is odd, then what will this string of cotangents, or what will this expression over here look like? Well, it is easy to answer that question because all we have to do here is replace n with 2m minus 1 and our powers of the trigonometric function of cotangent with their equivalents as we analyzed over here. Let us do that. We will have sine of 2m plus 1 times theta, it's this guy, equals to sine of the angle theta raised to the power 2m plus 1 times 2m plus 1 over 1 for our binomial coefficient. We simply rewrote n as 2m plus 1 over here. But then what do we have for the trigonometric function of cotangent? It will be cotangent to the power 2. Here we'll write m minus 0 of the angle theta, right? Just as shown in the top line over there. Next, we will have minus 2m plus 1 over 3 as our binomial coefficient right here. And for the power of cotangent, we will have cotangent 2 times m negative 1 as the power of the trigonometric function of cotangent. Next, we will have plus 2m plus 1 over 5 for the binomial coefficient, 2m plus 1 over 5 and choose 5. And for the trigonometric function of cotangent of the angle theta, we'll have 2m minus 2 and so on. But now, all of a sudden, what do we see over here in the bottom expression? We see that each and every cotangent is raised to an even power. Here this power is 2 times something, here is 2 times something, here is also 2 times something, which means that if we tentatively put, for example, cotangent square of the angle theta as, for example, x, a real number, x, then what will we have as an equivalent expression over here? Well, we will have sine of 2m plus 1 theta equals sine of theta raised to the power 2m plus 1. And here we will have our binomial coefficients spelled as follows: n choose 1 x to the power of m minus n choose 3 x to the power of m minus 1 plus n choose 5 times x to the power m minus 2. It will be this character right here, minus, and so on. And now all of a sudden, what do we have? Now we see the light at the end of the tunnel because it feels like we are actually manufacturing the very polynomial of the shape shown over here. Except that now we need to manufacture the situation when the squares of the trigonometric function of cotangent will be precisely the roots of the now not mystery polynomial as our reinterpretation suggests. How can this be done? Well, let us think about it. If the angle theta sub m takes on any of the following values: 1 times pi over 2m plus 1, or 2 times pi over 2m plus 1, or so on, k pi over 2m plus 1, and so on, all the way to m pi over 2m plus 1. What is the advantage of having the angle theta take on these particular values? Well, the advantage of the angle theta taking on these particular values becomes evident if we analyze the behavior of the sines of this angle shown over here in this expression. Let us do that together. Let me erase this portion because you guys probably wrote it down, or if you did not, then you can rewind. And meanwhile, I'll need the room over here. Let us analyze what will happen to the sign shown on the left-hand side of this expression if the angle theta in that trigonometric function of sine takes on any of these values. For example, a typical representative for such a value will be k pi. To be pedantic, we'll write that k varies between 1 and m. Well, that is not a difficult task to carry out. We will write sine of 2m plus 1 times, for example, k times pi over 2m plus 1. And what do we see over here? Well, these 2m plus 1 and these 2m plus 1 cancel each other out. We arrive at sine of k pi, where k is a whole number that varies, as shown over here. And at the integral multiples of pi, the trigonometric function of sine vanishes. So this will be equal to 0. That means that if the angle theta takes on any of these values shown over here, then the value of the trigonometric function of sine shown over here will vanish or become 0. What will happen to the trigonometric function of sine shown over here? Well, that question is also easy to answer, because in this case, let us just forget about the integral power of that function and look at what happens at sine, let's say k pi 2m over 1. In this particular case, depending on the specific values of k and m, these numbers, by the looks of it, are under no obligation to be co-prime, so they may probably cancel each other once in a while. But the thing is that for no values of k and m, this, or reasonable values of m that are of interest to us, this will be 0. In other words, the single copy of the trigonometric function of sine in this particular case will not be 0. And if a non-zero real number is raised to, for example, integral power, then it will not be 0 as well. So the sign raised to the power 2m plus 1 will not be 0. As a result of this straightforward experiment, what can we observe? Well, if the angle theta in this expression right here takes on any of the values shown over here, then we already proved that the left-hand side of this expression will be 0. Let's write it down over here. It will be 0. What will we have on the right-hand side? On the right-hand side, we'll have some real number. Let's designate it with rho, which is never 0, times something that is shown in the square parentheses over here. So basically, again, back from middle school algebra, we have 0 as a result, and then a product of two real numbers, of which one is, as we shown, necessarily never 0. What does that mean? That means that whatever is in the square parentheses must be 0. And that precisely means that when the angle theta takes on any of the values shown over here, that forces this particular polynomial to vanish or become 0. And that precisely means that we manage to, as a matter of fact, I just noticed it now, guys. I apologize, it should be 2m plus 1, 2m plus 1, 2m plus 1. And that precisely means that under these specific values, our polynomial shown over here vanishes. And that again means that the cotangent squared, when it takes on this particular values, becomes the root, these values become the roots of this specific polynomial. So now the shape of this polynomial is actually recovered by us completely. We know the shape of each and every summand in this polynomial, and to make it slightly more neat and more official, let us write down that polynomial, maybe even over here. Let's write it down over here. So we now know that this precisely is the guy p. What will be the degree of this polynomial? It will be m. So this will be pm of x, this guy. And just to make it official, let's write down expression for p sub m over here as follows. The first binomial coefficient will be 2m plus 1 over 1 x to the power of m minus the binomial coefficient to m plus 1, choose 3, xm minus 1. The next summand in this polynomial will be plus 2m plus 1 over 5, choose 5, xm minus 2, minus, and so on. And what does that mean? That means that for the purposes of the solution of this problem, we have recovered enough information already. We have the most senior coefficient, and we have the next most senior coefficient in the now not mystery polynomial. So the only thing that remains to do now in order to name the synonym for the real number that is encoded in this finite sum is to crunch the numbers a little bit. Here, according again to this formula for the sum of the roots of a single variable polynomial. Let us do that. For the value of the next most senior coefficient, we have the negative sign over here times this negative sign. These two negative signs, or -1 and -1, cancel each other out. And for the answer, we have 2m plus 1, choose 3, divide by this coefficient, or 2m plus 1, choose 1 as the sum of our roots. I do not write down the sum of the roots. You guys understand what's going on here. This expression is precisely this sum. Now, we know, as a reminder, maybe I'll write it over here, that n choose k is n factorial over k factorial times n minus k factorial. This is a way to represent the binomial, coefficient n choose k. So by that formula, for the first binomial coefficient, we have 2m plus 1 factorial over 3 factorial times 2m plus 1 minus 3 minus 2 factorial times what? 1 factorial times 2m plus 1 minus 1, 2m factorial over 2m plus 1 factorial. Now, 2m plus 1 factorial and 2m factorial cancel each other out nicely, because the product of the first 2m numbers sits right here, right? This guy is what? 2m factorial times 2m plus 1. 2m factorial and 2m factorial cancel each other out, and we're left here for this guy with 1 over 2m plus 1. 2m plus 1. This factor survives in this manipulation, and in this particular binomial coefficient, what do we have? We have this 2m minus 2 factorial encoded over here, and the only thing that will be left over here is what? For this guy, I'll spell it out over here. It will be 2m minus 2 factorial times what? 2m minus 1 times 2m times 2m plus 1, here divided by 3 factorial times 2m minus 2 factorial. Again, there should be no mystery for this manipulation, because I simply spelled out the 2m plus 1 factorial in terms of the 2m minus 2 factorial. So we grab the first 2m minus 2 numbers, and then we complete this factorial with 2m minus 1, 2m, and the last number 2m plus 1. What do we see here? Well, this guy and this guy, these factorials cancel out. 3 factorial is what? 1 times 2 times 3. These two and these two cancel each other out. And what do we have here as the survivors? Here we have m times 2m negative 1 times 2m plus 1 divided by 3. And this is only this factor right here. We need to multiply this factor, this binomial coefficient, by the value, this is this guy, 1 over 2m plus 1. What do we see in the result? In the result, we see that 2m plus 1 and 2m plus 1 cancel each other out. And what do we have at the end of all this seemingly laborious manipulations? we have m times 2m minus 1 over 3. Consequently, let us write down the answer. Let me erase this. Officially, what we have found through the construction of a polynomial whose roots are precisely the given real numbers that are represented by the square of the trigonometric function of cotangent is the following. The sum of cotangents squared of k pi over 2m plus 1, where k varies from 0 to m. This is pretty much a way to spell out not the specific numbers, but the general numbers that we are working with. The sum of roots of this polynomial is equal to m times 2m minus 1 over 3, and this is a general result. We actually managed to do a little bit more than we had to, but now we can use the formula that we just did use for the specific case. What is that case? We're told that the number n in our manipulations is 11, and it's representable as what? 2 times 5 plus 1, which means that m is equal to 5. M is equal to 5. So we can write down the synonym for the finite sum that was suggested in this problem, with k varying from 1 to 5, as what? 5 times 2 times 5 minus 1 over 3. That will be what? 5 times 2 times 5 is 10. 10 minus 1 is 9. So 5 times 9 over 3. And that will be what? 3 and 3 that's packed into 9 cancel each other out. 5 times 3 equals 15. And we now can erase this question mark over here and confidently claim that the synonym for this real number that is encoded into this finite sum is also 15. This is reasonably amazing result, because not only the sum of perhaps wildly changing values of the square of the trigonometric function of cotangent becomes not just a rational number, but in this case it came out to be a whole number. Also, I do not want to overload this discussion with too much technical details, but what we witnessed over here is actually another problem-solving approach in disguise, which may be called as generalize and conquer. And we can perhaps quickly already formulate the essence of this approach. Try to generalize a given problem, solve a more general problem, like we did over here, and then reduce the solution of a general problem to a solution of the specific problem by plugging in the appropriate numbers into the general solution. However, our reinterpret and conquer idea that we apply to the solution of the problem is actually like a horn of plenty that keeps on giving. Not only we can quickly nail the sum that is given to us over here, but we can just as quickly nail the product of these squares of the trigonometric function of cotangent, and we shall do that next. Now that we have done a fair amount of beautiful work, let us finish the solution of this problem on a high note, and compute the product of the squares of the trigonometric function of cotangent. According to the Vietas formula, for the product of these roots, where k varies from 1 to what? Here, -1 is raised to the power, which is the degree of the polynomial at hand. Our polynomial has a degree of m, as shown over here. Consequently, here, for the product of our roots, we will have -1 raised to the power of m, where m, again, is a suitable integer that captures the fact that the natural number n is odd, times the least senior coefficient a sub 0 over the most senior coefficient a sub m, and we know precisely the shape of that coefficient shown over here. Because m over here can be, again, either odd or even, we need to analyze two cases in order to answer the question of what the product of roots at hand will be. As such, let us first think about the case when m is a number that is odd, or when m is representable as 2l plus 1 for a suitable integer l. Well, in that case, -1 raised to the power of m will be 2l plus 1, will collapse into what? In this case, -1 will collapse into -1. And now we need to find out the shape of the least senior coefficient in our expansion. That is not too difficult to do, because according to this expansion, the very last term will be the binomial coefficient n choose n. In this case, cosine of the angle theta will be raised to power n minus n, which is 0, which brings the cosine into the unity, plus 1. The imaginary unit I will be raised to the power of n, and the trigonometric function of sine of theta will be raised to the power of n. In other words, the least senior coefficient in this case will be n choose n times cosine raised to the 0th power 1 times I raised to the power of n times sine of the angle theta raised to the power of n, and the value of the binomial coefficient n choose n will be 1. So this guy will be 1, we know that much. The number n is represented as 2m plus 1, so I raised to the power im 2m plus 1 will be I squared to the power of m times I will be -1 to the power of m times I. But the integer m itself is odd, which means that in this case, this construct will collapse into what? -1 to the power 2l plus 1 times I, and this will be -I. But we remember that when we associate the summands from this expansion from the I-bound pile to the only and to the single, to the sole I-bound term on the left-hand side of this relation, then I will disappear, in which case it means that, well, we'll put roughly, so I0 actually will be -1 in this case. So we have the factor of -1 raised to the power of m as -1. A sub 0 is -1. So in this case, -1 and -1 cancel each other out and flip into a +1. And the inverse of the binomial coefficient 2m plus 1 choose 1 becomes, as we already did this exercise, 2m plus 1. Very well. Let us analyze the case when the value of m can be represented as 2 times L, or as a number that is even. Well, in this case, it is evident then, in this case, -1 to the power of m will be -1 to the power 2L will be +1, the positive unity. -1 raised to an even power will be +1. And in this case, for a similar manipulation for the least senior coefficient a sub 0, we will have a +1 over here. So a sub 0 will be associated with I, or it will be in the imaginary unit y multiplied by +1, which means that in this formula we'll have +1 times +1 over the most senior coefficient a sub m shown over here, and that means that result will be exactly the same, which means that no matter the parity of the integer m in this particular product, the result will always be 1 and the same, 2m over 1, which means that, let us erase our experiment over here and write down an official generic result. We have it for the product of the real numbers, each of which is a square of the trigonometric function of 2m plus 1. 2m plus 1, we have 1 over 2m plus 1. This generic result is also interesting, but it's not as amazing as the answer for the sum of our cotangents, because again, according to the middle school definition of the trigonometric function of cotangent, it is a ratio of two functions, and in the product, in this construct, we have a product of these numbers. So in a product of ratio, certain numerators and denominators can cancel out. So it is still interesting that the product of these real numbers comes out to be a number that is rational. In our case, we already know that m is equal to 5, and the product of cotangent square k times pi over 11, this time for a specific value of n, where k varies from 1 to 5, we get the answer 1 over 11. Again, the process of solving this problem amounted to us trying several ideas, avoiding the head-on or brute force attack on that finite sum, and that process of trying and failing precisely constitutes the process of thinking like a mathematician, looking for a successful, a fruitful idea that will allow us to unlock a solution of the given problem in an elegant and perhaps beautiful way. In this case, we managed to do that by reinterpreting the given real numbers as the roots of a mystery polynomial, and then, as if by magic, the Vieta formulas shown here give us the answer for the sum almost free of charge, provided, of course, that we had to put in the work to recover the shape of the polynomial whose roots are precisely the real numbers in the problem. The last segment of this episode is optional. It is an extra for experts and for curious travelers. If you're not interested in this information, feel free to skip forward to the next challenge. Here, however, we know that back in the season 1, episode 2, we observed that the process of studying a certain mathematical theory and the process of solving corresponding problems enjoy mutually beneficial relationship. That is, the initial study of the theory at hand allows us to solve basic or elementary problems, and the process of solving these basic and elementary problems tends to facilitate a deeper understanding of the corresponding amount of theory, which allows us to bite off the next more advanced amount of theory, which arms us with more advanced tools, which allow us to solve more advanced and more difficult problems. And the process of solving these more advanced and more difficult problems tends to facilitate a deeper understanding of the cumulative amount of theory, and on this good and positive vicious circle goes. And as a result of this exercise, we both develop or may develop a better understanding of the theory and develop our problem solving skills. However, a sobering question over here is the following: where did all these problems come from? Were they shipped to us wholesome from a parallel universe by superior beings? The answer, of course, is no. And so far, until the advent of the large language model AI bots, that is, all these problems were put together by us, by humans, by people. However, in my not professional opinion, the seemingly symmetrical processes, the process of constructing a problem and the process of solving a problem, is actually not symmetrical. These two processes are not symmetrical because it is much more difficult to construct an interesting and worthy mathematical problem than it is to solve one, for the following reason. In order to have a chance at constructing a worthy and interesting mathematical problem, the author of the problem must be in a very firm grasp and command of the local material around that problem is constructed. But that requirement is necessary but not sufficient. What that means is that if we are not in a firm command of the local mathematical material around which we're trying to build a problem, then there is absolutely no chance that we will come up with something interesting and worthy. On the other hand, if we are in a firm command of the mathematical material around which we're trying to build a problem, then it is still not a guarantee that we will be able to put together an interesting and worthy problem, because an extra secret sauce is required for that process to succeed. The author of such a problem also has to possess a certain skill, a certain taste, and a certain experience. The pinnacle of the problem constructing skill is the ability to put together problem statements or questions that other mathematicians find interesting and that other mathematicians may be willing to work on. For example, historically, the German mathematician David Hilbert was known for that specific knack. He was good at framing pivotal, if not defining, questions, answering which the development of mathematics unfolded. And sometimes in even academic setting, in college, for example, in later years, just framing a problem statement or just framing a question, forget about solving the corresponding problem, just putting a reasonable and interesting question together can be a sizable achievement. Now, for us right now, this is a very tall order. Our ambitions are much more modest. But as the corresponding pedagogical wisdom runs, it can be said that the process of studying the respective mathematical theory and the process of constructing problems Also, these two processes enjoy a mutually beneficial relationship. In other words, it is just as educational to attempt to construct mathematical problems as it is an attempt to solve these problems. But be warned, this is very difficult, and do not be disappointed if you can solve mathematical problems, but you will not be or cannot put an interesting problem together. This is a very difficult task. Now, if we go back to the solution of the previous problem that we covered in the previous episode, we may recall that that problem seemingly was about our friendly dwarf who is trying to earn his bachelor's degree in mathematics, turning the lights on the garland on and off. But in the process of solving this problem, we realized that there is more to mathematics than meets the eye, that every worthy mathematical problem consists of two parts. One such part is something that does not vary and constitutes the technical essence of the problem, and the other such part is something, the material that does vary and constitutes the irrelevant minutiae, precisely because the variance of this material does not affect the technical essence of the problem. And we realize that that problem is not really about a dwarf playing with lights, but it is about a fundamental elementary number theoretic fact that each and every perfect square has an odd number of positive divisors, and each and every not perfect square has an even number of positive divisors. Consequently, here lies another mathematical pearl, so to speak. One way to construct an interesting mathematical problem is to start precisely with a well-known mathematical fact, such as the fact that every perfect square has an odd number of positive divisors and so on, and try to reinterpret that explicit language in such a way that the result is somewhat mysterious but unwindable problem. And that is where the reinterpretation idea comes from. So what does it mean to reinterpret a given mathematical fact? To reinterpret a given mathematical fact simply means the separation of the explicit language that describes this idea from that idea. And at the end of the previous episode, we, if you remember, gave several ways to frame pretty much the same problem, but in a different language: raising and lowering flags, flipping coins, putting gold pieces into a jewelry box, and so on. As such is our friendly and informal advice. In your travels, you may also try not only to solve problems, but try to construct problems. And the process of constructing a mathematical problem is also very beneficial. Even if you fail, still the idea is that you will walk away from this experience with a deeper understanding of the mathematical material at hand. The next challenge will be a problem in mathematics. It will be numbered S2M1, and in that problem, using one 5-gallon bucket and one 7-gallon bucket, we're challenged to measure 1 gallon of water. This is it for the problem statement of S2M1. And we remember that there is more to mathematics than meets the eye. We know that first and foremost, mathematics is an art of telling a story. And on this channel, we're trying to learn how to think out of the box. Consequently, when you will try to solve this problem, try to peer deeper and see if you can invent or construct, synthesize, generate a story that explains how and why the required algorithm can be carried out. Because in this problem, we're looking for an algorithm or a description, or a finite description of a finite number of steps, which will allow us to measure 1 gallon of water using one 5-gallon and one 7-gallon bucket. This is it for this episode. Thank you very much for your time. Thank you for watching. I'll see you in the next episode and in the next season, season 2, where I will discuss the solution of the problem S2M1.